purpose of this video is to show you to demonstrate to you the arithmetic of the set theory. With the usual arithmetic that we know from school, the objects that we deal with are, well, at least initially, they are natural numbers: 0, 1, 2, 3, and so on, and 4, and so on. And we've got various operations we can perform on the numbers. For example, we can add numbers. We can consider a plus b, where a and b represent numbers, and we can also multiply them, and we can subtract them. Well, at least when a is bigger than 0, bigger or equal to 0. We can compare them, right? We can compare them by the inequality. That is no longer an operation, though, but it's still a useful ingredient of arithmetic, because very often we end up comparing two different expressions formed by the operations such as plus and multiplication. And we can also exponentiate numbers, right? We can raise a to the power b, and so on. Well, in fact, not much so on. If we just stick with natural numbers, this is basically all we can do. Already here with the difference, we've got a certain limitation, right? We can't divide. Sometimes we can, right? Sometimes we can divide when it's divisible. So when b is divisible, when b divides a, in other words, when a is divisible by b, this is how usually it's written, then we can divide. Otherwise, the result of the division is going to be a number that's not a natural number. So if we want to limit ourselves only to natural numbers in terms of not only the input but also the result of operation, then we have to put some restrictions on the variables for certain operations like subtraction and division. Now, this arithmetic has an analog, and in many cases it can be derived from that analog of arithmetic for sets. Now, something that kind of mimics the specific objects of 0, 1, 2, and so on in set theory are the sets empty set, then the set singleton consisting of the empty set. So that can be seen as an analog of 0 and 1. But now after this, we have two different possibilities to continue on. We could take a singleton having the previous set as the unique element, or we could take the singleton, or we could take the two sets put together, right? So we didn't have such two options there. From up to 0 and 1, we had immediately two. Now we have two options for the next layer, and we have even more options for the further layers, among which will be the set having the second option of each of the, the first two options, the first two entries, and the second option of the third entry. So this is what I mean, this set. So this will be one of them. But there will be also other sets we can form using the previous ones, such as, for instance, this one. And so on. So you see, in set theory, we have much more ingredients than we have in arithmetic, and they're not linearly arranged as the natural numbers are. Yet, part of the philosophy of this being more is that we can represent the natural numbers as certain types of sets, and so then we can use the notation we have for natural numbers for representing various objects of set theory in a shorter way. If we denote this set by 0 and that set by 1, and then this set by 2, so now 2 is the set of 0 and 1, right? So that element is 0 and that element is 1. So 2 is the set consisting of 0 and 1 as elements. And then we can call this one 3. And if we notice here, we've got, what are the elements of 3? So 0 is the element of 3, that thing which was 1, and that thing which is 2. So every n would be a set whose elements are 0 up to n minus 1. So this is how we can encode numbers as sets. And one of the nice things about this encoding is that the number of elements in n is exactly n, right? If we start counting from 0 to n minus 1 and including 0, we will get n many objects. But keep in mind that in set theory we have much more objects than just these ones, such as for instance this one that didn't get assigned a label and that one. But now with these labels we can still have a shorter way of writing them. For instance, we can think of this as singleton having 1 as its element, and we can think of that as a set having 0 and singleton with 1 as its elements, and so on. So this type of notation, 0, 1, 2, and 3, and so on, is going to be convenient in set theory, because we can then refer to various different objects in an abbreviated way. Otherwise, we would have to write out these long expressions all the time. Now, on the arithmetic side of set theory, so we've got operations as well, and there is something that we call union of two sets that kind of mimics addition. So only in those cases when the two sets don't overlap, they don't have their intersection is empty, in other words, then the number of elements in the union is going to match with the sum of the number of elements in X and the number of elements in Y. So in a way, union mimics addition, but not quite. Then we've got Cartesian product that mimics multiplication. Then we've got set difference that mimics subtraction. We also have another one, the notion of a symmetric difference. But keep in mind that symmetric difference is actually expressible in terms of the other operations, namely union and usual difference. But then we have more operations that we not necessarily have here. For instance, we have intersection, and we actually have okay, so from this picture you might say that now on this side we've got exponentiation and division that we don't have here. We actually do have it here. It's just that we learn about it later on in set theory. Specifically, to learn about exponentiation, first we have to learn what functions are between sets, because it will turn out to be that a set raised to a power another set is just a set of functions from the other set to the first set. And for the quotient of numbers, to generalize that to sets, we would have to know about something that's called an equivalence relation, and also a different name for it in a different mathematical representation is a partition of a set. But at this point we don't have those tools, so we're going to ignore these operations. We're just going to stick to the operations given by intersection, union, Cartesian product, and difference. Keep in mind as well that the union and the intersection operations are also defined for arbitrary collections of elements by writing them as unary operators. So we've got these things as well in set theory. But in a way they're kind of still similar to the other one. We could have also argued here that we can take finitely many numbers and add them. The difference here, of course, is that here we can take union or an intersection of infinitely many elements, not necessarily finitely many. So now, drawing back to the analogy, if we kind of don't really distinguish between the finitary and the infinitary union intersection, basically what we've got here is union for addition, a Cartesian product for multiplication, difference for subtraction, and one other operation that doesn't seem to have a counterpart for numbers. Whereas relationships, we still have a counterpart for less or equal, and in set theory we can think of it as being a subset. And indeed, in this representation of numbers, if it turns out so that n is a subset of m, it means that, because remember n is the set of all the numbers strictly below n, so this being a subset of m means that all the numbers that are strictly below n are going to be also strictly below m, and that will force n to be less or equal to m. So there is a really nice analogy between less or equal for natural numbers and subset inclusion for sets. And now the next step after this is to look at basically the calculations, the computations we can perform using these set theoretic operations, just like when we learn about natural numbers and the operations on them, we end up dealing with a bunch of exercises where we are supposed to evaluate certain expressions of numbers, such as, for instance, 1 plus 3 multiplied by 5 and subtracted from it 4 times 7 and things like that. So we can do such manipulations also in set theory, and that will be a subject of a different video. So in this video, the point was to show you the analogy between the arithmetic for natural numbers and the arithmetic for the world of sets.